one of the Sentinel Earth-observing satellites. They occupy low Earth orbits that take them over the poles. In similar orbits, the swarm satellites monitor changes in the Earth's magnetic field. In a much higher orbit, the GOES weather satellite hovers above the United States. It orbits at the same rate that the Earth revolves. The New Horizons probe does not orbit anything. It was launched on a flyby mission past Pluto, and it continues into the Kuiper Belt. Satellites are expensive. Designed to operate at extreme temperatures in the vacuum of space, they cannot be maintained. They must perform faultlessly for years. Yet every satellite depends on the brute force and precision of a launcher to deliver it to an exact orbit.
Top.
Launchers are expensive too. They have varying capabilities and varying reliability, but new developments in rocket technology are changing what can be achieved and how much it will cost. The days of giant state-owned corporations launching their own satellites are over. Rocket builders sell their services to commercial or government clients. In October 2014, an Antares rocket built by Orbital Sciences was set to ferry supplies to the International Space Station. The launchers are generally reliable, but space is difficult. There is still a 7% failure rate. This fundamental step of leaving the Earth's surface relies on a small group of international companies that build heavy-lift rockets. The most iconic booster in operation today is the Russian Soyuz. It's not the biggest or most powerful launcher, but its history stretches back to the earliest days of space exploration. Variants of the Soyuz launcher have been in continuous production since 1957, and they have made more than 1,800 trips to orbit. Since the demise of the space shuttle, the Soyuz remains the only human-rated launcher in operation, and both ESA and NASA rely on it to ferry people to and from the International Space Station. It is a direct descendant of the Vostok launcher that sent the first man into space. On the 12th of April 1961, Yuri Gagarin rose to orbit on Vostok 1, designed by Sergei Korolev. The design, featuring a central core surrounded by 4 strap-on boosters, was originally conceived as the first nuclear missile. But as Soviet warheads became lighter, the launcher was adapted for manned trips to low Earth orbit. Today, 4 variants of the Soyuz launcher are in operation, and they launch from 4 different sites. Many of the simple design features in the Soyuz have contributed to its reliability and low cost. It was estimated that Russia could launch 20 expendable Soyuz carriers for the cost of 1 space shuttle launch. Though the basic layout of the Soyuz is still recognizable after 60 years, it has evolved. The design has seen several generations of engine upgrade, with the guidance system continually being refined. Final assembly at the launch site sees the 4 distinctive boosters flanking the central core attached first. In Russian, they're known as carrots. Each booster and the core have one rocket motor discharging through 4 main fixed chambers. For guidance, the boosters have 2 additional small swiveling nozzles on their outer edges, while the core has 4 guidance nozzles. With the boosters and central core united, the assembly is now lifted onto its specially adapted railway truck. At this stage, it weighs just over 20 tons. When it's fueled, it will be more than 250 tons. The 4 boosters are known as the first stage. Even though they ignite at the same time as the central core, that's known as the second stage. Then, if the assembly is taking place in Russia or Kazakhstan, the third stage and the payload are fitted. This is the gamma-ray astronomy satellite Mikhailo Lomonosov, being prepared for the first launch from Russia's new cosmodrome at Vostochny in Siberia. The launcher and satellite are all assembled horizontally, a technique that is straightforward and practical. At Baikonur, the original Soviet launch site still leased by Russia from Kazakhstan, rollout usually happens at dawn. Baikonur is the only launch site where the Soyuz can carry a human payload. All of the Soviet Union's history-making flights started from the Baikonur Cosmodrome. The area's sparse population was one of the main reasons the Kazakhstan location was chosen. The rocket is delicately moved towards the firing ring, where it will be held in place by the 4 tulip petal arms. It takes about 1 hour to bring the launch vehicle to the vertical. As the lifting arm withdraws, the 4 support arms are joined by fuel and electrical umbilicals and 2 halves of the service gantry. Ground staff will have access to every part of the launcher, and the cosmonauts will enter their spacecraft via this gantry. Technicians will spend the next 2 days checking the rocket and preparing it for launch. When fully loaded with fuel, its weight will increase by a factor of 15 to 305 metric tons. Soyuz carrier rockets also launch from the European spaceport at Kourou in Guyana, and from here the rocket is erected without its payload. Because of the equatorial location, the Earth's spin makes it easier to reach orbit. A Soyuz launched from Kourou can lift considerably heavier payloads to orbit than it could from a Russian launch site. However, Kourou's tropical location has 10 times the annual rainfall of Baikonur, and a mobile gantry that protects the rocket is necessary. Like the other European launchers, the satellite is attached to the Soyuz while it is vertical. 5 hours prior to launch, the fuel is gradually introduced. The liquid oxygen boils at minus 182 degrees C, and it is constantly replenished. At 36 seconds, the first umbilical mast retracts, leaving the rocket on internal power. Soon after, the fuel connection swivels away, and the turbopumps begin feeding fuel and oxygen to the engines. The engines are closely monitored as they are gradually brought up to full thrust.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, top, décollage, lift off.
A guidance computer in the third stage maintains the launcher's attitude via the vernier nozzles around the first and second stage chambers. Near the 2-minute mark, the boosters shut down and are jettisoned. At 85 kilometers, the payload fairing splits and falls away. 5 minutes after liftoff, and at a height of 169 kilometers, the third stage takes over to accelerate the satellite and its upper stage to escape velocity. Less than 10 minutes after launch, the upper stage guides the satellite to its designated orbit, while the rest of the launcher falls back to Earth. The American Delta IV Heavy is designed to orbit massive payloads or to hurl probes out of Earth orbit at incredible speeds. When it first flew in 2004, it had the greatest lifting capability available. The first and second stages, as well as the 2 boosters, are all powered by cryogenic hydrogen and oxygen. It can lift more than 28 metric tons to low Earth orbit. The Delta IV Heavy is made by the United Launch Alliance, a collaboration between Lockheed Martin and Boeing. It was designed to meet US military requirements. It has launched 2 NASA missions, but its other 8 launches have been classified reconnaissance satellites. Services have not been sold to commercial clients. Recently, a Delta IV Heavy was prepared for perhaps its most significant launch. It was mated with the Parker solar probe and its star upper stage. The Parker probe will be the first satellite to fly into the Sun's corona. And though its launch weight of just 685 kilos may seem puny for such a large launcher, Parker must leave the Earth's orbit at near record speed. After a brief period in a parking orbit, the second stage reignited to break the bonds of Earth's gravity. The final kick, delivered by the solid-fueled upper stage, gave the Parker probe the second fastest departure from Earth, and with the help of the Sun's gravity, it will reach 668,000 kilometers per hour, making it the fastest man-made object ever. In 2001, SpaceX founder Elon Musk hatched a scheme to establish a greenhouse on Mars and began trying to buy a Russian launch system. The space industry laughed, but they're not laughing now. Because he couldn't buy a rocket, he built his own. Musk knew American launches were too expensive, and a little research convinced him he could undercut the established aerospace giants. In design and manufacture, SpaceX focused on simplicity and reliability, with a view to keeping costs down.
Of the Falcon 9 rocket and the Dragon spacecraft, packing science and supplies for the International Space Station, humanity's home in low Earth orbit.
In 2012, SpaceX flew the first commercial resupply mission to the International Space Station. SpaceX designed its own spacecraft, the Dragon, to carry out these resupply missions. To date, SpaceX has completed 11 successful supply trips to the ISS, with 7 more booked. Unlike all the other cargo ships that visit the space station, the Dragon is capable of returning to Earth. The Falcon 9, the company's workhorse, was criticized because it has 9 separate rocket motors. Old rocket engineers argued that there were too many moving parts with a higher risk of failure. The Merlin engine, developed for the original Falcon 1, continues to be refined, giving the Falcon 9 a steadily improving lift capacity.
Past the speed of sound, it's now subsonic.
Soon it became clear what the multiple engines could achieve. Without its fuel load, the spent first stage falling back through the atmosphere was very light, and just one engine could enable a soft landing. If this worked, it meant reusable stages would drastically cut the cost of launches. A pinpoint landing on a remotely controlled barge required so many new techniques, and space experts were skeptical. A landing leg had collapsed and was redesigned. Soon, these return trips were routine. Though landing capability reduced the maximum payload by 30%, it also drastically reduced launch fees. Next came the Falcon Heavy, essentially 3 Falcon 9s strapped together. In 16 years, SpaceX had gone from laughingstock to builder of the world's most powerful launch vehicle. This first flight was to be a pure demonstration. Its dummy payload was Elon Musk's red Tesla Roadster. The car would go into orbit around the Sun. The plan called for the 2 boosters to land back at Cape Canaveral. The central core would return to a barge at sea. Potential customers were watching the demonstration closely, and crowds who gather along the Florida coast to see a launch now wait to watch boosters returning. The car, rigged with cameras, went into a solar orbit, but in the mission's one failure, the central core missed its barge. The US Air Force will be the Falcon Heavy's first paying customer. The entry into the launch market of a company aggressively trying to reduce the cost of access to space is changing the space business. Today, SpaceX remains the only launch provider that openly publishes the cost of its services. The Ariane 5 is the European Space Agency's heavy lift rocket. It features a liquid oxygen, liquid hydrogen first stage, flanked by 2 solid fuel boosters. Though the Ariane 5 is not the most powerful launcher, it holds the record for heaviest payload to geosynchronous transfer orbit. The equatorial launch site in Guyana makes orbits of low inclination easier to achieve and is an attractive feature for paying clients. The Ariane 5 ECA is the 5th and final version of the 5 series, which will soon be replaced by the Ariane 6. A new version of the Vulcain rocket engine is being developed for Ariane 6, which will be cheaper to build and to launch. New facilities are being constructed for the Ariane 6 at the Kourou spaceport, including a new vehicle assembly building which will see a change from vertical to horizontal integration. But the Ariane 5 still has much to do. 18 launches are scheduled before its replacement begins flight testing. The stages are fabricated in Europe and cross the Atlantic by ship. At the launch site, the central stage is raised to the vertical. Slightly more than 30 meters long, the core stage is essentially a fuel tank divided into 2 compartments with a rocket engine at its base. Each solid fuel booster arrives on its table in an upright position and preloaded with propellant. The upper stage, that will on this mission deliver 4 Galileo navigation satellites to their target orbits, is fitted. The satellites, clustered about a central dispenser, are then attached to the upper stage before the fairing that protects them during the trip up through the atmosphere is lowered into place. The Ariane, on top of the launch platform, begins its journey at a snail's pace. The Ariane 5 is operated by Ariane Space, who have launched more than half the commercial satellites in operation today. Russia's heavy-lift Proton launcher started its life in 1965. It was originally designed to carry a 100-megaton thermonuclear weapon to targets in the US. It was never deployed as a missile, instead evolving into a successful heavy launcher. It delivered several modules to the International Space Station, and one of its recent high-profile successes was the launch of the first ExoMars probe. But the Proton has not been without its problems. Developed during the Soviet era, its manufacturer Krunichev was reliant on the Ukraine for key components. And when launched from Baikonur, the Kazakh government was not keen on the extremely toxic hypergolic fuel it used. There are claims that acid rain falls after some launches, and that parts of Russia and Kazakhstan are being poisoned by the unsymmetrical dimethyl hydrazine that powers the Proton. At Baikonur in July 2013, a Proton M was set to launch 3 Russian GLONASS navigation satellites. An investigation found that the rate gyro package had been installed upside down. It was not the only recent Proton failure, and questions about quality control were being asked. Though the Proton still has launch commitments for several years, it will be phased out. Startup company Spacelab is poised for its first commercial launch. Their rocket, called the Electron, can deliver light satellites to low Earth orbit at prices that completely undercut the rest of the market. The launcher makes extensive use of carbon fiber in the construction of the tanks, and Spacelab has developed an engine with a radically new fuel cycle. Named after physicist Ernest Rutherford, the engine is largely constructed with 3D printing techniques. The liquid oxygen RP-1 fueled unit uses brushless electric motors to operate its turbo pumps instead of pre-burning fuel for the same purpose. The batteries powering the process add weight, but they save on fuel and give engineers finer control when throttling the engine. The launch site on New Zealand's North Island Mahia Peninsula is perfect for the busy schedule that Rocket Lab envisions. With the advent of microsatellites, smaller carriers like the Electron are becoming an attractive launcher for a new area of the launch market.